Yeah, hi, good morning, guys. Here we are.
User disconnected from your
Oh,
channel.
someone's disconnected already. On the 16th of August 2020. Just a short presentation, really, on how to try to understand or unconfuse some of these codes that you've seen as far as meta weathers. Um, this is a website that I've been using for years and years. I don't know whether you can make it out on the top there as far as the address, but I do have it here. Um, is that big enough for you guys to be able to read that website there?
Yep.
Yes.
Yeah.
That's fine.
Okay. Now, on some browsers, on mine, if I try the Hotel Tango Tango Papa address, it comes up unable to locate. But if you do a search either for Metar Decoding in Europe, it will come up this website and it comes up with exactly the same address. Or what you can do in the browser, woodair.net/aviation/meta htm, that will bring it up. So your browser will bring up that address for you. So if you want to see it for in the future for reference, that you got it there. Okay, gents. Okay, so this Bones Aviation, it originally started down in South Africa. They moved it, you can get into, it's a pretty good website actually. You can follow those links down the side. Can you see my cursor, by the way?
Yes.
Yeah.
Okay,
Yeah.
and I've made the arrow a bit bigger so that you can probably see where I'm going. Okay, METAR decoding in Europe. Well, first of all, there's basically two types of METAR reports. About 80% of the METAR reports around the world are in the European style, which is what we'll be looking at. And the other 20%, God bless them, is the American system. But that's used in other countries, like Japan use the American system and, whatever. So the basic MET reports, I'll just scroll down here very slowly. Hopefully it won't. There you are. I got to move that window so I can see it. Oh, there you are. You can probably see some of yourselves on the right, can you?
Yeah.
Yeah, okay. Okay, basic MET reports. So it comes down to, on these reports, it's broken down into a TAF, which is the forecast, aerodrome forecast, and the METAR, so meteorological actual or aerodrome reports. And the METARs are given, as you can read here, it's given, issued every 30 minutes. Well, sometimes yes, if there's no major changes, they can go on and it can be for longer than 30 minutes. But it's given a report giving the actual weather conditions at an aerodrome at the time of the report. And METARs are issued every 30 minutes during the opening hours of the aerodrome. He goes on to say here that he will not be decoding the TAF messages here, but will concentrate on the METAR. The codes used in both, however, are broadly similar, and it should not be difficult to decode the TAF. If you want to, we can have a look at a TAF at a later date. He's quite right. The codes are exactly the same, but what they do is they give you time frames. So say like today, it would be identified by the METAR for Echo Golf Kilo Kilo on the 16th. Then it will have the time, and then it will give the codes for the types of weathers, but it would give you time frame. So it would say the 16th from 1800 to 2000 it will be this, and then it'll even roll over into the next day for a 24-hour loop. Okay. As far as the identifier of the components, you're probably well aware of this, but on a METAR it starts out with the locator indicator. So the 4-letter, I'm going to have to put you over here. Oh, lost you. What have I done here? Oh, I'll get rid of that. I don't need that. There we are. Sorry, guys.
But we can see the thing all right though, Dave.
Okay, yeah. I'll actually, perhaps if I had to move it out of the way for my scroll wheel here, or for my bar rather. Okay, so yeah, the Metar Decode. So identify components. So first of all, it tells you what type of report it is, Metar or TAF. Then the 4-letter designator to the airport. Then on item number 3 here, it says time of the observation in UTC, Zulu, GMT, whatever, in hours and minutes, followed by the letter Z, Zulu, for universal time indication. So the example is, so they've actually, it's that they're showing Metar for Echo Hotel Alpha Alpha Mike, Amsterdam at 10:50 Zulu. If that was produced today at 10:50, it would actually have the 26th. Okay, so it identified the day number and then the time. The Metar weather components, you no need to actually memorize it, but there's an awful lot of what I call trigger points, so you'll be able to recognize what's going on, but they are in this sequence 1 through 10. Wind, visibility, RVR, weather, cloud, dew point, temp dew point, QNH, recent weather, wind shear and trend. Now if there is no wind shear, they don't report a negative. So no wind shear, there'll be no wind shear information. It's only presented if it is available. If there's an RVR problem, it will not present RVR. It won't say RVR nil. It just won't present any information. Second. Okay, back with you. Okay, so let's look at a typical example for the Metar. As I say, it's missing the day number here, but you can imagine that being there. So Metar for Amsterdam, 10:50 Zulu, 240 at 15 knots, 9,000 meters, rain scattered, 2,500, broken 4,000, 10 degrees, dew point 9, QNH 1010, and no significant. The trigger points on this, guys, is you can actually know what's going on. We've seen the sequence 1 through 10, and that's how it's presented there. Now if you look for knots, you know that's something to do with wind speed, don't you? So there you go, 240 degrees at 15 knots. There's a trigger. A 4-digit number, that's always the visibility. 4 digits is the visibility. So that goes from 0, 0, 0, all the way up to 9999. Rain, well, we'll be having a look at that in the coding. These are the different cloud layers. You can have more than one cloud layer. So we've got scattered and broken. We'll see this a bit later, but don't worry. 10 and 0 and 9 is okay. QNH and no sig. So we will follow these trigger points as we go through. He goes on to say here, note here, not all of the 10 weather components are shown. If no data is recorded at time of observation, that certain fields like the RVR or wind shear may be omitted altogether. In addition, the cloud component may be used more than once if the cloud layers are present. Okay. So, I think you continue at the moment for more detailed description of each field and come back to the Metar for Amsterdam at the end. So you guys will be able to read it just exactly the same as I did just now. Okay, because it's at first, when you first see them, it looks a bit of a mystery and it all looks gobbledygook, but hopefully this will clear it up for you. So number 1. This is a very dry subject, guys, so bear with us. It'll be worth it at the end. Wind is given as direction in degrees true, followed by the average wind speed. Now there's an old saying, if it's written, it's true. If it's spoken, it's magnetic. So what does that mean? Well, when you say like with active sky and you're getting the winds at different altitudes, this all comes from the meteorological balloons. But all of the reference there is done by true north. Okay, but when you're told it by ATC or by tower, they're giving you wind directions to magnetic north, which makes a lot more sense to the runways, of course, because they're magnetic. So sometimes you can see reports for airports, but it is in a true. But for all intents and purposes, we're not flying in too many regions where it's, the variation is up to 20, 25, 30 degrees. We don't get into too many conditions like that. We might be 3 or 4 degrees off of true north anyway. So here is the example here. So look for the trigger point. An example of the wind is look for the knot, the KT. So 240 degrees at 15 knots. So from the southwest at 15 knots. Kilometers per hour or meters per second may be used. Just a quick rule of thumb, if it's meters per second, whatever they say is in knots, just double it. So in that condition there, they would say 240 degrees at 30 meters per second. Okay. If the wind is gusting, it will be shown by a further group of figures preceded by the letter G, Golf. So the example, 240 degrees at 15 knots gusting to 27, indicates the average wind is 15, but it gusts up to 27. So it's gusting an extra 12 knots. When the wind is calm, then 0 degrees will be shown. A variable wind direction will be shown by VRB, Victor Romeo Bravo. So an example of that would be variable 2 knots would indicate the wind was only 2 knots, but it's not blowing from any fixed direction. If a wind is greater than 3 knots, there's no exam at the end of this, guys, but I'm just trying to share a little bit here with you. If it's greater than 3 knots and the direction varies by 60 degrees or more, then the actual value must be recorded. If the wind is greater than 3 knots, I would say that. But example, so 310 at 15, gusting to 27, but it's variable between 280 to 360. So the wind is blowing from the northwest at 15 and gusting to 27, but the wind direction does vary between 270 and 360. Pretty horrible day. It sounds like another airport to me. But there you go. Okay, visibility. Visibility. Here's another trigger point, guys. When you see 4 digits together, you know that represents visibility. So visibility as a 4-figure group in meters. Now European style Metar is always in meters. The American is in statute miles, and it's identified by Sierra Mike, SM. So there you go. 2,000 meters is roughly 1 nautical mile, as opposed to 1,500 meters is to a statute mile. Okay, the metric equivalent of a mile run is a 1,500 meter run. So 0000 is shown indicate it's less than 50 meters. 9999 is shown indicates a visibility of 10 clicks or more. If the local conditions vary greatly, then 2 groups may be displayed by the visibility variation in different sectors. Example, 1,000 to the northwest and 6,000 to the south shows a visibility in the northwest of the aerodrome 1,000 meters and 6 kilometers to the south. So ideally we can kind of figure out what to do there. In the event of this number being 1,500 meters or below, but then an RVR, a runway visual range, will be presented. So runway visual range is an indication of real visibility measured down the runway either electronically or manually. RVR is taken when the met visibility, the one just above, number 2, drops below 1500 meters. So it will therefore only be shown occasionally in the METAR. RVR will always be prefixed by the letter R following the runway number for which the value has been taken. So even though in this example you can see Romeo 24, it looks like runway 24, but the R doesn't actually represent runway. It stands for an RVR report for runway 24. So RVR for runway 24 is 1200 meters. Once again, European is always in meters. This is as far as the performance really and the legality of flying in these kind of conditions. RVR value recorded is significant for pilot operations. If the RVR value is below that published on the approach plates, or it's old habits, approach procedure, then the aircraft cannot make an approach. The aircraft must either remain in the holding pattern until the weather improves, or if you're getting tight, you got to divert. Okay, the RVR, when they're talking about this being published on the approach procedures, on the approach plates, like for the ILS or NDB or whatever, you've got the minimum altitudes. Perhaps that might be a subject for later on about charts. But on the minimum altitude on the charts for the type of approach, you will notice also there is a distance required. So what's advertised in the airport has to be greater than what's on the chart for the distance required, let alone for the altitude or decision height, the MDA or decision height, also for the distance. Otherwise, legally, you cannot make an approach. Now, this is not only for airplane safety, but this is actually a value written in by the aircraft manufacturers. They say, you know, below this amount, or this, if it's less than this distance, we are not certifying the safety of the aircraft. It's all to do with legalese. Okay, they have to draw a line somewhere. Okay. We are.
Can I ask a question on that?
Yeah, certainly. Go ahead, Trev.
What about Cat 3C? Does that still apply?
On Cat 3C, well, yes, it does. It does, Trevor. First of all, you have to be able to go into an airport that is capable of accomplishing Cat 3C arrival procedure. Well, not arrival, approach procedure. If you look now down in the bottom box, Cat 3C, you will see that actually you need 0 feet for decision height, and it will say 0 for the RVR, won't it?
Yep.
So as long as the RVR is greater than what's written down in the chart, you can do a legal landing. So that chart is saying that you can land legally in a 0 feet decision height and a 0 feet RVR, or down to 0 feet.
Yep.
Okay.
Yep.
And just thinking now, is there any offshoot off of that? I don't think so. If I think of anything else, I'll follow it up a bit later, Trev, but I think that's about it at the moment.
No, that's fine. Thank you.
Okay. Weather. Weather is identified by one or more 2-letter groups. The full list is not very long, so I shall include them here, even the more obscure phenomena. Now, I think he's joking, but I think some of us have actually managed to get a handle on some of these codes. Like, some of the codes to me make immediate sense, but others do not, like drizzle, rain, snow. Golf Romeo for hail, well, that's a bit of work. Squalls, yes. Small hail, don't know. Snow grains, well, you know, but some of it, mist BR, FG for fog stands out, FU for smoke. I guess that comes from the French, what is it, fume?
Fume?
Yeah, thank you, Dominic.
Or the Italian?
Yeah, exactly, yeah. But as you can see, some of these codes. Now, what I'd done actually, what I'd done was I just copied and pasted all of these, and I put it onto a notepad, and just printed them out, so that for some of the more obscure ones that we don't see too regularly, you know, at least I got a bit of an idea what's going on. But after a while, you start decoding, you know, 10, 15, 20 different metars, you'll be able to go through these pretty slick. They can also break it down. We may also describe these in more detail with 2-letter fixes. So it can be MI for shallow, patches, drifting, blowing, showers, thunderstorms, or whatever. And they can further describe it with slightly or heavy conditions, may also be described by using a negative or a plus sign before the 2-letter code. Examples, well, here we are, here's some of the codes. So here's a plain code, RA for rain, but here's now a mixture of the SH is showers and rain, so rain showers, FZ freezing, FG fog. Here we have a negative, so that's meaning a light drizzle. The next one is heavy, showers, snow. Shallow fog, CB, cumulonimbus, and TCU, a towering CB. Okay, but that looks an awful lot, but after a little bit of time you'll be able to recognize what those codes mean. Okay, gentlemen, and here we are. So we're on to cloud now. Cloud, this is usually a 6-figure group, and one that most you're almost already recognize. The group consists of 3 letters that describe the cloud cover, followed by 3 figures, which is the height above aerodrome level. So if I said, I don't know, few at 300 feet, when you're at sea level you can expect to see the bases to be at 300 feet above sea level. But if you're landing in an airport at 5,000 feet, you can expect to see the bottom of the cloud at 5,300 feet. So remember, the cloud is representative above the aerodrome level. It is not relative to mean sea level. They've broken this down into 4. I tend to think of this actually as 5. And a little bit of an imagination here, guys, for you. If you can imagine a clock with 12 o'clock being gin clear, clear of cloud, you've got 100% blue, clear blue sky, or 100% stars for the darkness time. But that's 12 o'clock. At 3 o'clock position, or a quarter way around the clock, that they call that few. In the old days it used to be called octas. I don't know if you can recall the weather briefings on BBC, and they're talking about the different regions around the UK, and actually I believe they still do it. I think they give the weathers in octas, but in aviation that's been dropped now. So the octa values you can forget about. But few to me represents if there's 25% cloud and 75% clear blue sky, that is what they consider few. Scattered is the 6 o'clock position. So half blue, half cloud, that's what they consider scattered. Broken is the 9 o'clock position. 75% cloud, 25% clear blue sky, and overcast back at 12 o'clock position. That's my 5th position. I've added the sky clear to start with, but overcast means 100% cloud coverage. Of course, there's the intermediates. Sometimes it can be between few and scattered, but in that case, they would quote the worst condition. But if you can imagine those kind of percentages, so when you're reading the information, not so much at the airport you depart at, you can do it at the departure airport, but you can see what the cloud condition is. But it gives you a good heads up of what it's at your destination and at your alternate or alternates. You may possibly have two. Cloud height is given by the next 3 figures, which show the altitude in hundreds of feet. Now this can catch people out. So all you need to do, whatever numbers are given, where are we? Here we are. See if I can highlight that. Whatever numbers are given there, just add 2 zeros at the end of it. So that would be 20, add 2 zeros, 00, 2,000 feet. And there's our code for scattered at 2,000 feet. Another one, broken at 500 feet. And overcast at 25,000 feet. 250, add 2 zeros, 00, 25,000. A metar may contain several cloud layers, so you may get scattered at 2,500, broken 7,000, and broken at 12,000. That's going on, that's repeating that again. So, sky clear, I think we understand what that means. They only break it down into few, but they can give you a code saying sky clear. That's why I tend to think of that as being the 12 o'clock position and gin clear conditions. So sky clear may be used if no cloud layers are observed. Well, that's good. CAVOC, you may have come across or you may see this. That stands for ceiling and visibility is okay. Now to qualify that, they have to have a form of qualification. So if these conditions are satisfied, they give you CAV-OK. Visibility is equal to 10 clicks and the lowest visibility is not reported. Fair enough. No cumulonimbus or towering CBs, no cloud below 5,000 feet or the highest minimum sector altitude. Don't worry about that one. And no weather, significant weather. So as long as there's no significant weather, no clouds below 5,000, 10 clicks viz, they give you the CAV-OK. Ceiling and visibility is okay. CB, oh sorry guys, I'll move that down a bit for you, or up a bit. CB, used to emphasize the cumulonimbus formation. Of course, that around you stay well away from it. Tango Charlie uniform used to signify towering CB formation, and NSC signifies no significant cloud exists above 5,000 feet, as opposed to CAV-OK was below 5,000 feet. In the conditions of fog, when the cloud cannot be seen, then the vertical visibility will be using the Victor Victor as a code. So example, Victor Victor 03, vertical viz 300 feet. If the fog is so bad that no measurement can be taken, then you may see Victor Victor / / in the metar. Okay. Temperature and dew point. Temperature and dew point are both measured in degrees C. A minus value is preceded by the letter mic. M for examples. Normal temperature at 25 degrees, dew point 12. But if on another day, tuck in the middle of it, well, probably in the springtime, 0 and -2 for the dew point. Now why do we need to know this? Well, the weather is not only giving us as airmen, as pilots, to fly these aeroplanes, but it's to give you a visual and information about current conditions, because current conditions interfere with the atmospherics, which have a direct input to the performance of the aeroplane. High temperatures, low lift. Low temperatures, high lift. Low temperatures, low thrust. High temperatures, low thrust. Low temperatures, high thrust. And it's the same with temperature and dew point. The temperature has an extreme measurement on the performance of the aircraft lift-wise and for engine performance. The dew point is a little bit more misleading. Some of you may possibly have the add-on where it creates pressure envelopes above the wing or on the intakes of the engine when you say at the end of the runway. That mist formation is created because the temperature and the dew point are very, very close together. As the aircraft is moving very, very slow or stationary and you go full power, air is actually being sucked in to the engine. And if the temperature is below, well, I'll tell you a bit about my experiences over in Canada, and they certainly got experience with freezing. But as the air is coming in, it's now a negative pressure in the engine intake. And once the temperature and the dew point approach one another, that then creates mist or moisture. An example is you get out of your car and go into a shopping mall in the middle of summer and your glass is mist up. Or you take a really icy cold beer from the fridge and take it outside on the patio. If there's a high dew point, in no time at all you get moisture build up on the can or on the glasses. Whereas when there's a big temperature range between the temperature and the dew point, it takes longer for that moisture to be created. Now, I said about Canada. Over in Canada, as far as application of engine anti-ice or wing anti-ice, well, wing anti-ice is more or less when it's visual on somewhere on the aircraft, so you do that. But as far as the engines are concerned, we always used to use any temperature below +10 with visible moisture. So visible moisture, what's that mean? Immediate clouds, the runway's wet, there's snow drifts either side of the runway, visible moisture. As soon as you start to put the power on, you're going to get those pressure envelopes. You'll be able to see the white clouds in the engine intakes. And on takeoff you'd have it over the wings as well. But what are you going to do if there's no visible moisture around? Over in Canada, I worked with four different operators, and all of them had a condition. In clear conditions, if it was below 10 and the temperature and dew point were within 6 degrees, you used an engine anti-ice because of that example. When the aircraft's stationary, you could possibly create icing in the engine just through the fact of being at high power. Once the aircraft starts to proceed and it gets faster and faster and faster, the engine is no longer sucking engine, the air is being rammed into the engine intake, so that cloud would disappear. So I hope that hasn't confused more than tried to give you some information, but that's the relevance of the dew point. Okay. Oh, 1 minute. Having a blonde moment here. QNH. QNH is rounded down to the next whole millibar, reported as a 4-figure group preceded by the letter Q. If the value is less than 1,000, then the first digit will be 0. So examples are Quebec 0996 or Quebec 1030. So once again, it's telling you the 0996, you're not going to be producing as much thrust as what you would on a standard day. And the 1030, you're going to be producing more thrust than on a standard day. And the wings, and also the aircraft lifting weight capability is influenced by this. Also, the weather condition gives you a good heads up. You know, like we've been talking about engine anti-icing, you can tell where the cloud layers are, so you can anticipate, do I need engine anti-icing on takeoff? Will I be going through clouds? Is it icing expected there or whatever? Also, you can check that for at the other end. They're reporting clouds. What altitudes are they at? Can I expect icing? Yes, I can. Now, all of this comes up into your decision on how much fuel you're going to take. If you think you're going to be in heavy icing conditions, throw in an extra fuel for those conditions. To explain this further, may I just add QNH values yet. Okay, QNH. I don't know if you recall, gentlemen, when I done this presentation a long time down at the old cafe there, I had a little picture, and I've managed actually to find it again. But I'll just finish this and then we get into the picture. Just add QNH value on your altimeter, then the height displayed on the instrument will be the height above sea level. If you are on the ramp, then your altimeter should read the airport elevation. Then the next bit is talking about QNH and temperature and pressure. Here they're just talking about the pressure. But here we are. Here's an old picture. Oh, I'll try to move this down. Do you remember this picture, guys? Okay. So here I am out in my little sailboat representing mean sea level. And then we got a cliff, we've got a 100-foot cliff, and then there's Dave Baggs Aviation Park on top of the cliff. Now, all elevations around the world are given heights above sea level, above mean sea level. And that is done at a standard pressure. It's called the ISA, International Standard Atmosphere, and those parameters are 1013, well, decimal, but 1013 millibars or hectopascals. Don't worry about millibar hectopascals. It's exactly the same measurement. It's just the parameters of how they managed to create it. And or the American system, which is used in America, Canada, Japan, as I mentioned earlier on there, they use inches of mercury, 29.92 inches of mercury at 15 degrees C. Now, as we mentioned earlier on, temperature and pressure has a big effect on engine performance and aircraft performance, so there has to be a standard set somewhere. So these are the standards set and recognized internationally. This is ISA, ISA. We can talk about that a little bit later. So, if today's current pressure QNH is 1013, and I dial in 1013, in the airport, at the airport in my aircraft, the altimeter should read 100 feet. If we're in a high pressure zone, where like on the weather forecast you see the millibars, you know, the circles going around, it's high pressure or low pressure or whatever, you adjust the altimeter to the local area QNH. So regardless of what the pressure is, if you dial in the local pressure QNH, the altimeter will read 100 feet. Now we fire up the engine, we do our engine run up, and we launch off and we climb. So here we go now, we're climbing. Once we reach an altitude, you make what's called a transition it's called a transition. At a specific transition altitude, you change from the local QNH pressure to a standard pressure. So above the transition altitude, you now change the altimeter to 1013 or 2992. So that now I'm in an area, a volume of air with all aircraft above transition altitudes, they're all relating to the same atmospheric pressure of 1013. So when I report I'm at flight level 350 and somebody else reports they're at 360, we know that we are exactly 1,000 feet away from each other on a standard pressure setting. Okay? So it doesn't matter who is up here, as long as they're above the transition altitude, they should be on standard pressure, and everybody can then relate to each other altitude-wise. For altitude distances is all going to be exactly the same. So we go out, we climb up to 10,000, well, flight level 100. We scoot around, fly all around the country, and then we want to come back in. Now on the way down, we're still on standard pressure, which is the ISA standard 1013 or 2992, and sometimes it's called ISA, sometimes it's called standard, and sometimes it's even called QNE. So Q is the coding for pressure, and the NE stands for nautical elevation, but it's not used too much, but you may see it. But everybody's on standard pressure until they hit the arrival transition level. Once you go below the transition level, you now dial in the local QNH, which is what you get from your weather briefing. A way that I tend to, some people get confused. They think that the outbound is the TL and the inbound is TA. The way I remember it is transition altitude. Well, transition by definition is a state of change. Transition altitude, well, if I have a state of change and it's referencing altitude, I have to have altitude set for me to be able to make the transition. And altitude or height, any reference to altitude or height is always with the QNH, whereas on the way down, transition level, it's a state of change. I have to be in a transitional level setting, which is standard. So you have to maintain standard pressure to that transition level, and then below that, then you go on to the QNH. Or another way of remember it is TA, if the A stands for airborne or going above, and TL for landing or going lower. So hopefully that'll help you. Nice little airport, that. Okay, let me.
Dave, is the difference between the transition altitude and transition level normally around about 1,000? So in other words, if you're at 6,000 TA, then your TL is 7.
Trevor, there's different conditions for different parts of the world. I tend to relate to what it's like in the UK.
Yeah.
The towers make up the transition altitude. Altitude is normally set up by the plates. The transition level is assessed and created by the authorities on the day. Now it all depends on the pressure, whether it's high pressure or low pressure, but generally if you look at about 1,000 feet difference, that's very much a ballpark figure. Yes, it can be, but having said that, some parts of the world the transition altitude and the transition level are exactly the same. A good example, United States of America, Canada. TA is 18,000 feet. See the feet? That's QNH related. But coming down, the transition level is flight level 180, 18,000 feet. But that's 18,000 feet on standard pressure, not the QNH. But the actual numeric value is it's either the same or it can be different. I'm quite sure Jonathan will be able to bring us totally up to speed on the reason why, but I know it's pressure related. But say like for Canada or the States, potentially if it's a high pressure, that's going to interfere with the altitude, the true altitude of the transition level.
Sorry to interrupt.
No.
Could whoever's making their Sunday lunch please mute their microphone?
Here.
Okay,
Thank you.
okay. Bon appetit. Okay. Yeah, where was I? Yeah, the transit, it's not so much a problem going up because you're relating to the QNH from the airport that we've just taken off from Dave Baggs Air Park here. So that transition position is going to be pretty constant. But on the way down, the transition level, that transition level for actual true value above the ground is going to vary on the pressure of that day, because you're set on standard pressure, so you're going to be higher or lower. If that badly answers your question there, Trev.
It does, because on charts you often see the TA shown on the chart, but TL it will say by ATC.
Yes, exactly. And sometimes they don't even give you that. What they can do is, like, if you're reporting in, say, flight level, well, let's say 100 or 10,000 feet above sea level, or flight level 100, and he clears you to 6,000 feet. Well, the feet is the trigger that you go into QNH, but then he will say you're cleared to 6,000 feet on QNH 1017. So sometimes they don't know. Also, I've seen it in ATIS. Like we're talking here about METARs. ATIS, the Automatic Terminal Information Service. They sometimes give you transition levels in those reports, but we don't. As simmers, we don't tend to use ATIS. Well, other than when you go on to VATSIM or IVAO. Okay, Trev.
Thank you.
Okay, so I hope that's helped a little bit. Either that or I've totally confused you all the more.
Nope.
Number 8, recent weather. This may be included if appropriate, using the weather codes before, prefixed by the letter RE, Romeo Echo for recent. Example, recent rain, RE, RA. Hope you're starting to recognise at least the RA part of these codes. You'll be able to pick that one out. Wind shear. This is another one that will only be included if appropriate. So this is an example of it. Again, this is only included if appropriate. The code Whiskey Sierra is used, followed by the runway affected example. So you've got Whiskey Sierra. LDG is landing, runway 28 left. Or if turbulence or wind shear has been reported, say on a previous takeoff, they give you wind shear takeoff runway 08. And here we are. So number 10, you'll be glad to hear. Trend. This is only available at selected airfields. It is intended to indicate significant weather changes of weather in 2 hours after the observation is made. If the change is temporary, then tempo, that's pretty good shortcut, is used, followed by the predicted conditions. If the change is permanent, well, then becoming, once again pretty appropriate, will be used. So towards the end of the Metar report, as we will see in a second, here it says no sig, and as you can see, the original Amsterdam no sig. So the trend temporarily is 4-digit number. So there's a trigger point. We know that's visibility, SH showers, RA rain, and look at this, visibility 3 clicks with rain showers. Becoming look at the trigger here, KT, so we know they're talking about wind and direction. So 330 at 35 knots, becoming 35 from 330. Very good. And no significant weather. Well, no significant weather, no significant changes. So hopefully now with some of those explained, let's have a look at some of the examples. First, we'll look again at the Amsterdam. So for some of you, I might have rushed through it a little bit fast, but that's how quick you can get with some of this coding. You can actually see what it is. So Metar Amsterdam, it should have the date. So today that would be 16/10/50 Zulu. Here's my trigger, knots. So 240 at 15 knots, 4-digit number. We know that's visibility. If that was less than 1500, you'll remember, we can expect to see an RVR report. So 9 kilometers RA rain, scattered at 2000, add on 2 zeros, 2500, broken 4000, 4000, temperature 10, dew point 9, and 1010 QNH, and no sig. So hopefully that is starting to make a little bit of sense. That's just explaining exactly what you would see. Okay, sometimes a Metar can be quite brief sometimes. So here's one. Once again, it's missing the date, but I think you got the trend of what I was saying here, guys. Metar Echo Golf Lima Lima, good old thief row, 0920 Zulu, KT, we know what that means. 260 at 5 knots, Cav OK. So just to reiterate, that means ceiling and visibility OK. So ceiling, there's no clouds below 5,000 feet. There's no precipitation, and visibility is 10 clicks or greater. So rather than reporting all those conditions, they're saying that Cav is Cav OK. 15 degrees, dew point 14, QNH 1013. So it's standard. It's a nicer day. 15 degrees at 10:13. No significant. On the other hand, where are we? Here we are. On the other hand, in bad weather, a Metar can look very much different. So these are the ones we don't like to see, 'cause you have to make decisions. Have a look at this one for Dusseldorf in poor visibility. We will see the conditions. Metar Dusseldorf, Echo Delta Delta Lima, 1550 Zulu, 260 at 5 knots, 0550. So the visibility is 550. Do you remember the 1500 rule? Less than 1500, you have an RVR report. So that's why we got R, which stands for RVR, not runway. I know it looks like runway, but I'm just it represents an RVR measurement. So 23 left is 450. So what does this mean? Now when you're checking in your charts and you're doing an ILS or a VOR approach, visual approach, you have to look at the visibility requirement to do that type of approach. So anything greater on the chart, greater than 450, you can't do an approach. FZ freezing, FG fog, and that will become apparent in a second. Sometimes they make mistakes on the Metars. God forbid them, we never do. Overcast at 200, not 2 feet, 200, 2 zeros added. Now here's the temperatures. Temperature is -2, dew point is -2. Well, do you remember I was saying about when the temperature and the dew point get very, very close to one another? This is when the moisture condenses. Well, when the temperatures are the same, you will get fog. You can get not only fog when it's freezing, you can get fog when it's 20 degrees. 20 degrees outside, dew point 20, you will have fog. So the freezing fog report is actually supported by the temperatures. Now if that was -2 and the dew point -12, the freezing fog can't be. One of them has to be wrong. QNH 0994, low pressure, low engine performance. Mind you, it's very cold, so then you get a bonus in engine performance. Becoming, so what they're saying is, after this reported time, up to 2 hours afterwards, it's becoming overcast at 500. So it's currently at overcast at 200. Now, most ILSs, it's 200 feet above airfield. So you're really marginal to do an ILS in these conditions. A Cat 1. You could do a Cat 2, which is 100 feet, or a Cat 3, or 3A is 50 feet. And then, of course, it gets less and less and less, like Trevor's Cat 3C is down 0, 0. But if it was really marginal, say for an ILS at 200, you may choose, because it's telling you it's becoming overcast at 500, so then that opens up your 200 above the airfield. It opens that window up quite nicely. Or, in its current condition, you'd have to do at least a Cat 2 or a Cat 3 to land, if the airport is capable. Of course, if you haven't got any or enough fuel to hang around, you might have to hang around for a while. Call up tower and see when they're expecting it to go to 500. You might have to scoot off to your alternate. Here's one for Dublin. It's going to be a question for this one, guys. So look out here carefully. Here is one for Dublin. Metar for Dublin 0900 Zulu. Yeah, horrible day here really. 240 at 35, gusting 55. The winds are variable between 210 and 270. 1700 meters, so it's above 500, so we're at 1500, so there's no RVR expected. Plus SHRA. Plus is heavy, SH showers, RA rain, heavy rain showers. Broken 700, so a Cat 2 would be fine. Overcast 1500 CB. Well, that's pretty horrible. Temperature 8 and dew point 7. So with those temperatures and with the cloud base and with the current weather conditions, would we be having engine anti-ice on or off for landing?
On.
Yeah, exactly. Well done. It's less than 10 degrees with visible moisture. So yeah, there's visible moisture, all right, because they're saying there's heavy rain showers. So you couldn't expect to have engine anti-ice on. So it's no big deal for simmers really. It doesn't really matter. But these are the reasons why this is all included in the report, so that the crews get a pretty good heads up. So there'd be a mental note, or there'd be a sticket stuck on a gauge somewhere saying, "Don't forget to put the engine anti-ice on plank." And so that's that. And then it goes on to say, temporarily a tempo 3500, 4-digit number. We know that's visibility. So it's telling you that the visibility is increasing from 1700 to 3500. So now, gentlemen, my question is, what is missing? Something very important missing from that Metar coding.
Yeah, QNH.
Exactly. Well done. Who was that? I didn't see who that was, but anyway, well caught. I had as I said, I used to use this website for when I was back at Fly UK doing a little bit of training there, and I'd done this maybe 5 or 6 times, and then the next guy he says, "Where's the QNH?" I hadn't even recognised it, but he's 100% right. Yeah, on that one code, it's missing the QNH, which of course is important. So anyway, well done. You get a cookie, whoever that was.
Dave, you were talking about low temperatures of and dew points producing fog, and you alluded to the higher temperatures. I presume you're talking about places like the Gulf where you get higher temperatures and high dew points.
Well, in places like the Gulf, yeah, the current temperature would be above 10 degrees, wouldn't it?
Mm.
So as long as the temperature is above 10 degrees, there is no need for any engine anti-ice.
Yeah, no, I wasn't talking about the anti-ice. I was just talking about the case that you were using it as the lower temperatures, but the higher temperature ones would be more particular with Gulf, wouldn't it? You'd see in the Gulf.
Oh, yeah, regardless of the temperature outside, if the temperature and dew point are within, well, we used to quote 6 degrees, whether 6 degrees is the actual amount, I don't know. You just go by procedures. It could be 4, and they say, okay, for safety-wise, we'll add another couple of degrees. But regardless of what temperature it actually is, if temperature and dew point are very, very close to each other, in suction or in negative pressure zones, you will get that pressure envelope where it creates the fog.
Mm.
I've seen it at the Dubai Air Show.
Mm.
Like you wouldn't assume that dew point is, very high, but occasionally they do get fogs there. But I've seen it at Dubai Air Show with some Air Force team flying. And whenever they done the flyby, you got the pressure envelope on the upper surface of the wing.
So, Dave, during a flight, is a pilot constant, or the first officer constantly referring to these predictions?
Oh yeah, yes, Frank, you are. Of course, at the start of a flight, well, depending on the length of a flight, of course, you can tend to use the departure airport, the arrival airport, and the alternate airport. You can use that information all the way through. Of course, when you get to the other end, you'll be picking up the 80s, which may be slightly different, or it could be totally different to what you were given an hour or 2 hours or 3 hours ahead. On the majority of my flights, I'm looking at 8, 9, 10 hours. So, of course, I'm not looking really at the Metar at the other end. I'm more interested on the forecasts. So you will be doing that. But it's you can get updates of the destination airport as you're flying along. But also, it's not only the departure airport and the arrival and the alternate. You're also looking at possible divert airports en route. So as you're going overhead Athens, you'll be checking the weather out there. So, 10 minutes further down the road, something goes tits up on you. Oh, I got the weather for Athens just now. They're gin clear. We can make it into there, dive into there.
Right, thank you.
Okay.
Yes, because I suppose, Dave, when you put, I know, like we do with SimBrief, it gives you an alternate airfield. Funny enough, Fly UK do, but of course, in reality, when you're flying, I guess there are many alternative airports, provided you can land on the runway length, etc., which you may have to use. It's only a contingency, isn't it? I mean.
Well, if you're talking about contingency as in contingency fuel, or whether you're just saying more or less as a bailout situation, you do look at airports or airfields that are considered primary diversion places, so that en route, you at least you got something to hang your hat on, so that you can make a plan to get back into. Not so bad, like a. Of course, a 2-engine aircraft, you have to land at the nearest airport or available airport, so that's fair enough. Three engine and 4 engine aircraft, as long as you've got enough fuel, you predict how much fuel you need to destination, you can continue, so that there's no EROPS operation required. But you know, there can be situations where you lose one engine, bad fuel, whatever it is, you may end up losing the second engine. We're now 2 engine on a 4 engine, you have to land at the nearest airport. So it pays to keep in contact with the nearest airports that are capable of taking you. Like, you know, there's no point looking at airports with grass runways, that ain't going to work. Or runways, airports with short runways. You'd be looking, in the worst case, every aviator's nightmare is fire on board. Statistically, you've only got something like about 13 minutes to get your ass off. Oh, sorry. But, so having an alternate airport, the weather, we just overflew Athens 10 minutes ago. We can spin around, get back in there. They got, you know, good firefighting equipment, so you know you can get into there. But it is reviewed and it's looked at all the time. Yeah, it isn't just a matter of sitting back reading newspapers and Sudoku, even though that is done. But you are working in crews.
Yeah. Okay. Thank you.
Okay. Yeah, go ahead, John. I think.
Yeah. Can you not just leave the anti-icing on all the time, or does that take fuel?
Yes, John. Can you leave engine anti-icing on all the time? To an extent, engine anti-icing is on all the time. They rely on the engine temperatures to actually keep the engine hot. The engine works more efficiently once the engine oil is up to temperature and you've got a consistent flame in the combustion chambers in there. Once that's stable, the engine is happy as Larry. Engine anti-icing is protecting primarily the engine intake, so there's a valve normally associated to allow air in onto the nacelle on the engine nose of the on the nose of the engine to keep ice free of there, but also the initial stages of the low pressure compressor, the initial stages of the front of the engine. Once the air has started to go through the engine, now the air, it gets compressed, temperature rises, so with the temperature rise, now it reduces the event of ice being created further down the engine. And of course, right at the back there where the flames are, there's never any ice there. So the actual physical temperature of the engine is continually keeping the front of the engine de-iced. In the event of temperature going below 10 degrees, plus 10 degrees with visible moisture, you can select engine anti-ice on, and that is to eliminate any ice build-up on the front of the engine in the front of the initial or the first stage low pressure compressor region.
Okay, thank you.
Okay.
So if you leave it on all the time, as John was suggesting, what is the effect? You're using more fuel than you would normally do.
Oh yeah. Thank you, Frank. Yeah, I meant to follow up on that. Well, for a start, above 10 degrees is not required, Frank. Above, if the temperature is already outside, it could, you could be in Dubai or Bahrain, like we was previously saying. You could be there and it's 35, 50 degrees, and you throw one engine out the ice. Now, those leading edge, the engine anti-ice vanes are up to 60, 70 degrees. There is no requirement for that, and also it's throwing in a temperature that's not required for that for those blades to remain ice free. But whenever you take engine anti-ice, for the engine anti-ice, which normally, as I say, includes the nose cowl anti-ice, you have to have that heat energy from somewhere, and that heat energy comes from different stages of the compressor. Now, if it takes X amount of air to go through the engine to be burnt to produce the amount of power to maintain an altitude or a speed, and you reduce pressure off at the compressor, there isn't as much air at a higher pressure going to be burnt. So to produce the same amount of thrust you need for altitude and speed, you have to push the throttles up. So it's a roundabout way of answering your question, Frank. To extract air off of the engine, you are actually making the engine work harder because you're having to push the engine thrust levers up, burning more fuel. And yes, that is a big penalty. So do you remember I was saying, when the pilots look at the weather, they want to know what the icing conditions are, so that they can make a pretty reasonable guesstimate of how much extra fuel they need, because now the engine thrust levers have been pushed up.
Would that explain some of John's crashes?
I would have thought they'd have actually been able to put a sort of electric wire or something around the front of the engine, which would be sort of come off the batteries rather than off the engines. See what I mean? To actually de-ice the front, or is that not feasible? I mean, you see how clever these engines are.
Yeah. Oh, yeah. Yeah. Like,
John, where do the batteries get their energy from? The engine?
No, they get them from the dynamo.
Yeah, where's the dynamo connected to?
Oh, I see what you mean. Yeah, okay, all right. We're going round in circles, in other words.
Yeah.
Actually, if I could just interject there, weight is a critical consideration at airlines, including something as simple as taking off a seat back tray table off the last row. Even British Airways will take those off to make savings in weight. And when you multiply that throughout the fleet and throughout the year, it's a significant saving. So to put something electrical on there, you're going to be carrying that weight for all the time, for probably only using it for a short time under certain conditions.
I can only say blimey to that, Derek. Those two trays you're talking about, relative to the weight of the aircraft, are like a fly blow on a gnat's knee, aren't they?
They are, but then you've got to multiply that by how many you're taking out, by how many aircraft you've got, and how many hours you are in the air, and it is significant. And they took them all off the last row of seats. They took them off. Like, David, you'll know that, won't you?
Oh yeah. Weight is a penalty that aeroplanes don't like. That's why they like the modern aircraft that are manufactured with more composite materials now. So of course, less weight. Aeroplane can go higher, but just going higher alone, you burn less fuel from the same engine. But now engine efficiency is increasing, so the aircraft can go, engines are happier, higher. Yeah, and also, the engine anti-ice and the airframe anti-ice, like I've been relating to manual. So in answer to your question, about electrical, and also I'm talking about aircraft that uses pneumatic air pressure, which come from the engines themselves, from the engine compressors. But there are electrical airframe anti-icing. They also use air pressure, like they have balloons on the leading edges of the wing, so they wait until they get a wing ice build up and then pressurize the balloons. They blow up, it pops the ice off, and then the balloons go down, and then off they go. Also, more modern aircraft, engine anti-ice and airframe anti-ice is more automated. You just turn it on to auto. Well, actually, some aircraft don't even have an auto switch. It's there automatically. It's just on whenever the aircraft senses engine anti-ice conditions, which is plus 10 degrees or less. It comes on automatically. I'm quite sure Dave be able to support me on that. I think the 777, it's auto engine anti-ice, isn't it?
Yes, it is.
Yeah. So there you go. Your idea, though, for an electrical heating, that could work on a nose cowl. Yes, it certainly could. I don't know how it would work for the engine vanes that are anti-iced, but I'm quite sure. It doesn't mean that it couldn't be done, John, but it isn't a normal format. But there again, I'm talking of aircraft types, well, primarily DC-8 747. I can't say for all aircraft types.
And there's no material that they could use that is anti-ice, not anti-ice protect, but will not get ice on it,
Well, that is correct. I guess the closest to a material where ice doesn't stick would actually be the synthetic crystal blades, but they are produced primarily for heat resistance rather than icing.
Thank you.
Okay. So, any other concerns or questions, gentlemen? That's the that's a little presentation that we had done it before many years ago, but I hope that's worked out for you.
Yeah.
Oh, excellent, Dave. Thank you very much.
Thank you, guys.
Yeah.
Very
Well done,
professional.
thank you.
Very, yeah.
Yeah, well done,
done.
Dave.
Okay, well, thank you all very, very much. Just to be first of all, thanks for turning up. It makes it a little bit better. Had a bit of a chat, and I'm quite sure, like myself, I've been thinking about Paul over the last couple of days. So I think I'll probably speak on behalf of all of us here. But we wish him well and fast recovery.
Indeed, indeed.
Is there any news on Paul?
Yeah, I have spoken to Paul. He remains very positive, and he said he should be out by the end of the week.
Oh, excellent.
Okay.
So he did email. I think he has hooked up his ECG machine with his computer, getting his emails through the ECG machine.
Nice one.
He did laugh at that. I can't get hold of his wife, unfortunately, but it's a shame because I'd like to support her as well, because she's obviously very worried and can't go in to see him. But he says she's okay, and he should be. We should be hearing from him soon, hopefully.
Okay. Well, very, very.
Thank
well,
you.
that's good news. Thank you. Thank you, Derek. That's great. Okay, well, I think I'll be wrapping this up. I'll be stopping the recording. As I mentioned, I'll try to get this up on the on our website, YouTube. I'm waiting to hear back from Jason on that. But just one other thing to share with you, probably might be a bit of fun. I don't know those who heard about Radio 1's thoughts on COVID-19, but I'd like you to join me in saying, COVID-19, up yours.
Definitely. Yeah.
Okay, take care, guys, and bye-bye now.
Thank you, Dave.
Dave.
Thanks, Dave.